Okay. So let's jump in and see if we can see if we understand these principles, how moving charged particles interact with fields, and how the resulting forces are realized. So what about this? I have a negatively charged particle placed in this magnetic field coming from this permanent magnet as shown. What direction is the force from the magnetic interaction acting on that charged particle? All right, I'm going to go ahead and end the poll. Share the results. Pretty spread out. We have a decent amount in all answers here. So let's think about this. We know that that force is going to be QV cross B. What direction does the magnetic field point? Well, those lines are indicating the field. So here the magnetic field is pointing in this direction. Okay. What direction does QV point? Well, QV points in this direction also, QV. Because I have a negatively charged particle, QV points in the opposite direction of my velocity vector. And now I can see B and Q and QV are aligned, right? So remember the magnitude of this thing is QVB sine theta. Theta in this case is equal to 0 because those two vectors are aligned. So that gives me 0 magnetic force. What if I switch this? What if I put a positive particle here? Let's redo this. What do you think would happen if I put a positively charged particle? Okay, let's end. More of you think that the magnetic force is equal to 0. Well, let's see. The only thing that changes is for a positive particle now, my QV is going to point in the direction of my velocity. And now what's my angle theta going to be? Well, my angle theta is going to be 180 degrees here. Sine of 180 degrees, still 0. I still have 0 magnetic force. Okay. The velocity has to have some component that's perpendicular to the magnetic field to generate a field. Or to generate a force, excuse me. I remember in a cross product, if I just think about it generically, A and B, the resulting vector C always points in this direction that's perpendicular to the plane defined by A and B. Well, if A and B point in the same direction or are anti-aligned, there's no plane defined, right? I'm just defining a line in that direction and I don't have a plane. So you always have to have some component of the two initial vectors in the cross product that are perpendicular to one another to generate a non-zero cross product. All right, let's think about this one. I have a negatively charged particle that has the velocity indicated by this green vector. What direction does the magnetic field have to point if there's an observed force that's pointing out of the screen at us, right? There's a force acting on that particle that's pointing out of the screen towards us. What direction does the magnetic field need to be oriented? Okay, I'll give you guys a few more seconds. All right. So most popular answer here by far is C, up and to the left. Well, let's check. Let's see if that gives us the right answer. So let's assume this is the correct answer for B. Let's use our right-hand rule. What direction does QV point? Well, I have got a negatively charged particle. So QV is pointing in the opposite direction of V. Right-hand rule says I align my index finger with the first vector in the cross product, my middle finger with the second vector, which is B, and I end up with that force pointing out of the page at me. Okay, so this works. So this is the correct field. All right, let's think about this one. I have a negatively charged particle here that has some velocity, and it's going to pass through the center of these two charged plates. And what I want to have happen is that this particle just makes its way straight through the center here without being pushed towards the positive or negative plate. In order to achieve that, what kind of magnetic field do I need to establish between those two plates? Okay, let's go ahead and end the poll. A lot of you selected the magnetic field should point downwards. Well, let's see. We know that FB is equal to QV cross B. But in this particular problem, there's another field present, right? This is a parallel plate capacitor, so we know there's also an electric field that's pointing down in between these two plates. And so this charged particle is also going to experience an electric force that we know is like Q times the electric field. So when this particle gets somewhere, say, in between these two guys, it's going to be experiencing, well, what direction does that electric force point? Well, this is a negative charged particle, so this is going to be like minus the fundamental charge times E. So that force is going to point against the electric field. So if I want this thing to just pass straight through the middle, right? If there were no magnetic field, we know what would happen. This thing would be pushed towards the positive plate. So I need my magnetic field to counteract that force from the electric field. I need that magnetic force to point downwards. I can use my right-hand rule to try to establish what direction it needs to point now. QV, what direction does QV point? Well, it's a negative charge, so vector QV points against the velocity. So I'm going to align my index finger with QV. My thumb is going to be that resulting force, and I want it to point downwards. And so that gives me that my index finger would have to point into the page for this particular capacitor. Well, that's a nice problem to think through because I have both the force coming from the particle's interaction with an electric field and magnetic field simultaneously, and I'm trying to come up with this balancing force to get it to experience zero net force as it passes through those capacitive plates. All right, let's think about this one. I have a proton, a positively charged particle, and it's being shot straight towards a wire that has current that's flowing into the board. So we're looking at the cross section of a wire, and the current is flowing into the page. What's going to happen to this charged particle as it approaches that wire? So while you're thinking through this, think about the magnetic field that the wire will generate and the resulting interaction of that charged particle. All right, I still see a few answers coming in. All right, I'm going to go ahead and end the poll now. A little split between B and D in this case. So let's think here. Let's find the magnetic field that's present where that positron is in this case. I'm going to use my right hand rule. My thumb is going to point in the direction of that current that's flowing into the board. My fingers are going to circulate around it, right? I have a circulating magnetic field that goes around it in this direction. So that means over here, the magnetic field is going to point upwards. And I know the strength of the magnetic field increases linearly as I get closer to that wire. So the strength of the magnetic field is going to be growing like this as I get closer, but the direction stays the same as I'm firing towards this wire here. What about the resulting force on that charged particle now? We know that the force coming from the interaction with that magnetic field is going to be like QV cross B. Let's use our right hand rule. QV, it's a positively charged particle, so it points in the same direction as the velocity. QV is our index finger. B is pointing upwards at that region in space. So my thumb is pointing out at me, so I have my force is pointing out of the board towards us. Right, so as that particle is coming in and moving across here, it's gonna, right, if you were watching this thing, it would start moving towards your face, so it would be coming out of the page, and it's gonna hit the wire, right? It's never deflecting up or down, it's deflecting out of the page, and so eventually it's gonna hit the wire at some point in front of the screen. Okay, what about this one? I've got a wire that I can drive some current through, and it's in the presence of a magnetic field that points into the page in this example. And there's a gravitational force that's pulling that wire down. What direction do I have to drive the current in this wire in order to generate a magnetic force that'll counteract that gravitational force? Okay, let's go ahead and end. Most popular was B here. Well, let's work through this. We need the magnetic force to point upwards to counteract the gravitational force. We know that F is going to equal to IL, right? This thing IL, right? This is just the same thing as saying I'm going to point my finger in the direction of the direction of the moving charge. Remember, the current is just flows in the direction of the velocity of the charged particles. IL cross B. So I need the resulting force to point upwards. I need my middle finger to be aligned with the magnetic field to point into the board. That means my index finger, it has to point to the right. And so I have current that's flowing from left to right inside of this wire. All right, let's think about that current carrying loop again. So here I've got this loop of wire and I'm passing current through it. Okay, so it points in that negative direction there. Or sorry, so it's circulating around. So current is flowing in on the left and out on the right. What happens to this loop when I release it from rest in the presence of this magnetic field? What kind of motion will it experience? All right, let's go ahead and end the poll. Most of you selected that it rotates counterclockwise. Let's go side by side. So over here, remember we have that F is equal to IL cross B. So the first vector points in the direction of the current, the second vector points in the direction of the magnetic field, and the third is the resulting force. So let's use our right-hand rule. On that left-hand side, the current is pointing into the board, the magnetic field is pointing to the right, and so my right-hand rule tells me that the force has to be pointing down on this portion of the wire. What about over here? Well, now that current is pointing out at me, the magnetic field, I've got to rotate my hand so that my middle finger points in the direction of my magnetic field. Then my thumb tells me the resulting direction of the force points upwards. Look, the sum of the forces acting on this ring are going to be 0, right? Some of the force points up, some points down, they counteract each other. There's no net force. But if I look at, say, a position about the center of this loop, well, there's a non-zero torque, right? The sum of the torques, both of those are providing a negative torque, right? It's going to be, right, in this case, some negative torque. This thing is going to want to start rotating in this counterclockwise sense. An alternate way you could think about this is, we know that if I take my fingers and I curl them in the direction of the current in the loop, then my thumb points in the direction of the magnetic field that's generated by that loop. And so I could think about that little loop of current, right, generating something that looks like a little permanent magnet. And so you could think about this kind of like a compass needle. Well, a compass needle is just a little permanent magnet that has a pivot point through the center. And what does that compass needle do? It always wants to rotate to align itself with the external magnetic field. So this, right, if I have two magnetic fields, what happens is they want to rotate the objects generating those fields to try to align the magnetic fields. So this thing again would have to rotate in the counterclockwise sense. That's the shortest path to try to align. That's the sort of the shortest path that would try to align those two magnetic fields. right? This is the fundamental principle that electric motors operate under. Right, you can see that if I can take current and get it flowing around in this circular path and place it around in an electric field, that it generates this torque and I can create an object that wants to rotate around. So that's exactly how electric motors are generated. Your book talks in details about the engineering or how you would design that system. But the basic principle is just this one. You want to take some current, get it looping around to generate this dipole form for a magnetic field, place it into an external magnetic field that wants to align those two magnetic directions and have the thing rotating around. Right? The engineering trick is that once this thing rotates around and the B fields align, the torque turns off. So the moment that the object gets over to this position, you would want to flip the magnetic field in the opposite direction, or flip the direction of the field, like flip one of the two fields so that it would want to then switch and align itself back the other way to continually spin. Right, but that's just you can look in your book the engineering solution to that part of this problem. Okie dokie. What else? Okay, so that's all I brought in for to go over in class today. So what we've seen is, right, this sort of fundamental